So we have a description of the armature. We're told it's a 6-pole, 600 RPM DC generator. The armature got 90 slots, each containing a single coil. So 90 coils. Each coil got 4 turns. We're given the total flux at 120 milliwebers. Calculate the voltage induced in the generator. So we know that the voltage induced in the generator is given by this equation here, and we need to before we can use it, we need to calculate Z, which is the number of conductors on the armature. So the description of the armature opposite side with that. N is simply the speed in revolutions per minute. Phi is the flux per pole. Now we're given the total flux, so we got to figure out flux per pole. And of course 60 is a constant proportionality. And so we start off then by thinking about the armature. And this formula here, okay, so it's giving me trouble with putting the two of them on there, and so now I'll just leave it at that. Okay, so now when you look at this, right, Z is the number of coils, and for our calculations we won't ever have more than 1 coil per slot. Now there's possibility to have different kinds of, there's lap wound and wave wound windings where some of them we'd consider to have 2 coils per slot. But for our calculations, we'll never have more than 1 coil per slot. So the number of coils really is the same as the number of slots. So we got 90 coils. The number of turns per coil and the number of conductors per turn. And if you recall the diagram that we had, which described the generator, and you can go back to page 40 for that, or you can look at the ones that where we did torque production in the motor, where we called it ABCD, and 2 of the conductors are parallel with the flux, so they don't of course cut flux, and so A, B, and C, D are the 2 conductors per loop or per turn. And so if you look at this as a kind of like a unit conversion, right, and calculate Z. So we have for Z then the number of coils, which is 90, and again, for us that's the same as the number of slots. So 90 coils multiplied by the number of turns per coil, and that's given, right, that's 4. So 4 turns per coil and again the number of conductors per turn is always 2, and you just got to remember that, I guess. Now and so if you made a sketch, of course it should be clear, and so here, right, coils cancels with coils, turns cancels with turns, and we are left then with conductors. And so when we calculate Z, now Z is equal to, if you multiply 90 times 4 times 2, the result is 720. So Z is 720 conductors. Now, N is given, and so we're left with phi. And so remember that phi here, right, is per pole. And so it's important to realize that here you've been given total flux. Now, remember that the poles occur in pairs, and so think about the fact that because the flux occurs in pairs, when we have the total flux and we want to figure out the flux per pole, it's the number of pole pairs that we divide by. And you know, if you sketch that, one of the easiest things to think about is that the idea is that, look, if I got a north pole and a south pole, that's a two-pole machine, and the flux comes out of the north pole, goes into the south pole. And so in that case, right, we would consider that the flux per pole and the total flux are the same. You know? So you wouldn't divide by 2 and half it, because the flux per pole and the total flux is the same. So in a 4-pole machine, right, the field looks a little bit different. And if we you know, we got this going on here, and the flux comes out of the north pole into the south pole, and so something like this, right? And so the idea is that, you know, we wouldn't take the total flux and divide it by 4 there to try to figure out what the flux per pole is. We divide it by the pole pairs. And so 1 pair up there and 2 pairs here, and so on for a 6-pole machine, and if there's more. So here we have a 6-pole machine, and so we have 3 pairs. And so the idea now is that the flux per pole, we could call it, is equal to the total flux times the number of divided by, rather, the number of pole pairs. So we have 120 milliwebers for total flux, and 3 pairs of poles. So we're going to divide that by 3 pairs. And so that gives us now 40 milliwebers per pole. And so we can call that as a decimal without the milli, 0.04 Webers per pole. So the numbers now that we need to put in: Z is 720 conductors, 5-pole at 0.04 Webers per pole, and of course the speed has been given to us. So E0 is equal to, I don't know if I can fit it in here, I'm going to give it a shot, 720 conductors multiplied by 600 RPM multiplied by 0.04 Webers per pole, and we're going to divide that by 60. 60 is simply a constant that comes from a conversion of radians per second to revolutions per minute, and that's where that shows up from. And so that calculation now has given us a voltage induced in the armature of that generator of 288 volts.